All right, buckle yourself in. This is going to be a long one. So we're going to go through and we're going to look at 6 different types of trends that we can look at in terms of ranking the strength of an acid. Try to figure out which would be a stronger acid and which would be a weaker. Now, these are going to be the most helpful when we're going to be comparing 2 different structures. And often, actually, in our practice problems, we're actually going to be looking at 4 different structures most of the time, and then kind of ranking them from 1, 2, 3, and 4, from most acidic to least acidic. Kind of like using a lot of these trends. You're going to see this on homeworks. You're going to see this on the upcoming celebration of knowledge and things of that sort. So when we're doing just a relative comparison, and we're not just going to look at pKa's, we're just going to focus on our structure. The one thing that we're going to look at a lot is going to be thinking about our conjugate base. If you are an acid, you donate or you lose your proton, you're going to be left with that lone pair and a negative charge. And if we can rank the relative strength of that conjugate base, the one that's going to be more stable is going to be the one that's going to be a stronger acid. And if you kind of think about that in a way of, if I'm going to have to carry that negative charge, if I can stabilize it really nicely, then I don't care about losing it because I can become a little bit more stable. So we're going to often think about our conjugate bases and how stable they are, and then using that as a gauge. So more stable conjugate base is going to tie to our stronger acid. So the first 2 trends are going to be kind of thinking a little bit more on our periodic trends. These are going to be ones that work really nicely just for kind of like really simple structures. And then the 3rd and 4th are going to be the ones that we'll kind of like use the most. So when we think of our periodic table, and this will be my attempt to draw the periodic table like super quickly. Cool, good enough. So here's our periodic table. We're going to first thinking about our trends from, that's not the right color, our trends from left to right, and then our trends from up and down. And this is going to be like number 1 and number 2. So as you move from the left to the right on the periodic table, you're going to increase your electronegativity. And if you are more electronegative, when we think like rules of resonance, we want to put that negative charge on the most electronegative atom. Kind of the same relative theme here. If we're going to have a negative charge, if I can put it on something electronegative, that's going to be better than on something that's going to be more positive, or have lower electronegativity. So if I look at like the kind of like second period of the periodic table of like carbon, nitrogen, oxygen, and fluorine, I could see CH, 4, NH3, OH2 or H2O more commonly said, and then like FH or HF more commonly pronounced, as each of those having kind of like 4, 3, 2, 1 as we kind of move from the left to the right. And in general, if I'm going to be more electronegative, I'm going to be a stronger acid. So something like fluorine or oxygen is going to be much more favored than something like carbon because they're more electronegative. Now, if you're fluorine, it's just HF, so we're primarily focusing on like the carbon, nitrogen, and oxygen. And our kind of like key focus here that we really want to focus on is putting having a hydrogen that's connected to an oxygen is going to be better than having a hydrogen connected to a nitrogen, which is going to be better than putting it on a carbon. So generally, abstracting a proton on a carbon is going to be kind of our lowest or our last choice, where our nitrogens and our oxygens, our NH2s and NHs are going to be more common, and then our OHs, our alcohols, are going to be even higher. Those are going to be our most acidic. So we're often going to be looking at kind of structures with like oxygens and nitrogens rather than carbons, and then our carbons are going to be at like our lowest tier. Now, we don't really move up and down the periodic table much because most of our stuff is just kind of like that carbon, nitrogen, oxygen range. But as we go down our periodic table, our size gets bigger and bigger and bigger. So if we think of just like our kind of simple like HF, HCl, HBr, and HI, fluorine being the smallest, and then chlorine getting bigger, bromine getting bigger, iodine getting bigger, just because we're adding more and more shells. You're getting an increase in your like total amount of orbitals that exist. So the ones that have the biggest type of size physically associated with them, the kind of like less impact of that charge it will have. So HI is going to be better than something like HF. This is kind of just thinking general size, like if you're maybe considering like a sulfur versus an oxygen or something of that sort. But this is a rule that we won't use too much, but you kind of think about like the bigger size is able to accommodate that charge better than a small, where that's carrying like most of the weight. Now, the two that we're going to focus on the most are going to be number 3 and 4. And these are going to be focused on resonance and then what is going to be known as our inductive effect. So let's go ahead and think about resonance. And as I said in our last unit, resonance is something that is never going to go away. We're going to see resonance again and again and again. If you have resonance, you can actually move that charge, that negative charge that would come from the deprotonation, to a variety of different atoms, and that will actually help stabilize. So here, we're going to have 2 different examples here, where we're going to have an OH. One of them is going to be as a carboxylic acid, and the other one is going to be as an alcohol. Already, if I just look at the pKa's, and here's where, like, if you have pKa's, you can use pKa's super easily and say, hey, pK of a carboxylic acid is around 5. That's going to be way better than the pK of an alcohol in that 15 to 16 range. Therefore, my stronger acid is going to be my carboxylic acid. Now, let's say I've totally forgotten my pK values altogether. That's okay, because I can actually just use the structures. So if we consider, let's go ahead and in each of these, let's consider an acid-base step where we remove that proton, so minus H+. Our product would then be, or our conjugate base, would then be that H gone and then having a O-. Same thing for our ethanol, having our O-. Now, if I look at the difference of my oxygens, these lone pairs on my ethanol, that's my one that's just the alcohol, are localized, meaning they cannot undergo resonance. I don't have any double bonds or sources of electrons that can actually do any resonance. So this is actually stuck directly on that oxygen, meaning that oxygen is going to carry that entire weight of that negative charge. Alternatively, if I look over at my carboxylic acid, I see that I have this single double structure where I can actually do resonance. So this lone pair can actually come in here to make a double bond and then push up to make a lone pair. This is actually kind of one of our very first examples that we actually gave you of resonance, where this would then give me my neutral and then my O- on that top one. So here in our first case, our carboxylic acid, instead of that charge being stuck just on that oxygen, that charge can be delocalized or spread apart across that oxygen-carbon-oxygen section. That's why sometimes we'll actually show that as like that dotted line going over that entire like set of atoms. So because of the fact that that negative charge is spread out around 3 different atoms rather than 1, each of them only kind of like feels it as like maybe a third or a half of a charge rather than a full. And that's going to mean that it's going to be a lot more stable of a conjugate base, meaning my original structure is going to be a stronger acid. So if I have resonance, that is going to be preferred. Resonance is going to help stabilize that negative charge. It's going to help give us a more stable conjugate base, and therefore the original acid is going to be a stronger acid, more likely to lose that proton. And this is going to be one of the major themes that we're going to see kind of throughout. Now, the next one is going to be kind of similar in the like effect, but we're not actually going to have any physical resonance. And these are going to be known as the inductive effects. And an inductive effect is going to be weaker than resonance, but it's going to be when you have a dipole that's going to help stabilize that charge through space. So often this is going to be when you have some electronegative atoms, for example, like a chlorine in this first one, that can help stabilize that charge by them just being super electronegative and kind of pulling that charge towards them. This is weaker than resonance because you're not actually physically moving it. You're just kind of lessening the load. You're kind of like using these electronegative things as kind of like a support network to kind of like help encourage you to not be so negative. So here, if I look at an example, this is actually the same carboxylic acid. And then instead of in our original, we have kind of like hydrogen, hydrogen, hydrogen. If I change that to chlorine, 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 chlorine is going to be extra negative. It has a high electronegativity, so it's going to want to pull electron density towards it. So there's going to be kind of some dipoles towards that chlorine. That is going to help. Not only are you going to originally have your resonance in both of these that are going to spread that negative charge across those 3 atoms, but by also having these chlorines pull, that's going to make these oxygens and carbon feel even less negative because that chlorine is going to pull some of that weight. And you'll see that pKa drop from around 5 to almost 1, below 1, I should say. And the amount of your electron withdrawing groups will actually, an electron withdrawing just means something electronegative, will actually impact that as well. So like if I wanted to show like a second structure where I do OH, if I did, for example, like let's say ClCl, where I just had 2 chlorines instead of 3, your pKa would actually be in between these at around 1.3. And then if I only had 1, it'd be between 1.3 and 4. So one of the things that we'll think about when we're thinking about our inductive effect is the amount. The higher the amount, the better it will be. One of the second things that we'll think about is going to be your proximity. So I guess we'll do, grab my pen here. So if I consider a few examples here, let's do the same base structure, and it will be this carboxylic acid with a few extra carbons. And if I, for example, have one that has no groups at all, it's just simply a carbon chain, there's a few more carbons, it's going to have a pKa that's going to be pretty close to 5. The exact value here is actually 4.87. If I put a chlorine way at the end, so really far away from where my H is, because my charge is going to sit kind of like over on this like oxygen, because that hydrogen is going to be the most acidic proton. The reason that's going to be the most acidic is it's connected to an oxygen, and oxygens are going to be much better at stabilizing a charge than a carbon. So if I put this chlorine really, really far away, it does decrease my pKa, meaning it's easier to remove because of the inductive effect, but it doesn't change it a ton. It drops down to 4.05. If I move that over one more, kind of put it closer, that's actually going to have a bigger impact, and that pKa is going to jump all the way to kind of like a 2.86. You don't need to know these pKa values, but just kind of like show like the relative like impact of that group. So having a chlorine is good, but having like, or something electronegative is good, but having it really, really close to your source is going to be better because it can feel it more. The last part of when we kind of think about the inductive effect will kind of be like our type. And that's going to be kind of think of like your electronegativity. So if I think of maybe like a kind of simple case here, let's just think of, again, just a bunch of carboxylic acids. We'll go ahead and do, I think I have 4 that are plotted. So if I look at these 4 different carboxylic acids, if at that same location, I put maybe, let's say maybe an iodine versus a bromine versus a chlorine versus a fluorine. So this is kind of iodine being lowest on the periodic table, bromine being higher, chlorine, and then fluorine being our highest on the periodic table. That's going to be an increase in our electronegativity. So our electronegativity is going to increase as we go from the left to the right. If I look at the pKa values, this one will actually have a pKa value of 3.2, where the bromine is going to be 2.9, and then 2.8 and 2.7 for the other 2. So as I become more and more electronegative, I'm going to have stronger inductive effects because I'm able to stabilize more because of my electronegativity. So if we kind of look at all of these in concert, if I zoom out a little bit. So Not as strong as resonance, but we can have the inductive effect, which is where we're going to have electronegative groups nearby where that proton is going to be abstracted, and that's going to help stabilize your charge. So more electronegative stuff at closer and more electronegative in general will all be ways in which you can get a stronger acid. So in this kind of like series of each of these, thinking more chlorines, chlorine closer, or moving to, for example, like a fluorine instead of a chlorine because it's more electronegative, are all ways that we can increase our stability of our conjugate base and therefore increase our overall acidity. So our inductive effect in resonance, either physically moving the charge or simply pulling it through a dipole, are going to be two of the major ways in which we think about our ways to stabilize. The last two are ones that are a little less common. The number 5 here is thinking about hydrogen bonding. If you're comparing something that has a ton of hydrogen bonding to something that doesn't have a lot of hydrogen bonding, the thing that doesn't have a lot of hydrogen bonding would be preferred. These are going to be ones when you have them tied on like the exact same atom, especially like inside a molecule. This is going to be intramolecular rather than intermolecular. So like if you're being stabilized a bunch by yourself, you have to kind of overcome that point of attraction and then go through and be deprotonated. So you have a little bit of extra work to do there. You'll see your OHs and your NHs a bunch. Yes, they have the ability to hydrogen bond, but overcoming those forces are a lot less compared to like the stability you can get by putting a negative charge on like an oxygen or a nitrogen compared to a carbon. So don't read too much into this one. Technically there, and you'll see it mostly just in an intramolecular case. The last one we'll see is thinking about hybridization. So when we think about our hybridization, I have examples here of a single bond, a double bond, and a triple bond. So that's our alkane, our alkene, and our alkyne when we think about our functional groups. Each of these will have different pKa's. When we're thinking of abstracting a proton, that's like, for example, this hydrogen, or this hydrogen, you'll notice that your single bond and your double bond have really, really high pKa's, about 45 and 50. Those are very rarely going to be used in terms of our acid-based stuff, but our triple bonds will actually be used. They're actually down at 25, which is kind of a nicer range. In general, if you think about hybridization, your single bond being sp3, your double bond being sp2, and your triple bond being sp, the amount of s character, and when we say s character, that's kind of just like the percentage of s orbitals that are involved. If you're sp3 hybridized, your s orbital takes about 25% of your overall structure, whereas we go to sp3, it's around 33%, and then at sp, it's around 50%. As you increase your s character, you have less hybrid orbitals and therefore more acidic. That higher amount of s character will help stabilize because it's going to lower energy. If we think of just our general energy, like we have maybe say a 2s and then our 2p, our s orbitals are going to be lower energy than our p's. So having high s character and less hybrid orbitals will help increase your stability. And I know that's a lot, and we're going to get some practice both in the next video as well as a ton in class. But here's just some of our general trends we're thinking about when we're just simply comparing two different structures. The main thing that we're trying to get to is which has the most stable conjugate base. In general, we're going to try to put our charge on something electronegative. Oxygens and nitrogens over carbons. If we have the ability to undergo resonance, that's awesome, and that will really help stabilize our conjugate base, and therefore our original structure will be more acidic. So resonance, really big. Nitrogens and oxygens, better than carbons. Inductive effect will be kind of our tiebreaker in between two, where if you have two that are super similar and there's just some minor differences, we'll then think about the inductive effect at the way in which it can kind of help stabilize just through your dipoles, which are going to induce a impact. This is going to be way weaker than resonance, so that's kind of our lowest tier. And those are some of the kind of thought processes. So we'll go ahead and end here, and then in our next one, we'll kind of do some practices where we look at, for example, here, a bunch of different structures, and then thinking about which of these, if we had to rank them 1, 2, 3, and 4, would be overall our best structures. So we're going to stop there, and I'll see you in the next one.